Oxetanes are four-membered cyclic ethers. Oxetanes are four-membered cyclic ethers. They are derivatives of cyclobutane. This is cyclobutane. When we replace one CH2 in cyclobutane with oxygen, we get an oxetane. So it is a saturated heterocyclic compound. It is derived from cyclobutane. So saturated oxetane is saturated heterocyclic ring. It is derived from cyclobutane by replacing one methylene with oxygen. So it contains three methylenes, CH1, 2, 3. Three CH2 groups and a oxygen. It is called oxygen. So four-membered ring is not common in nature. This oxygen is not common in nature, just like the acetylene. It is also not common in nature, but it occurs in some physiologically active compounds. Coming to physical properties, it is a colorless liquid having boiling point 47 to 50. This is not 80. This is 47 to 50. 47 to 50 degree centigrade. It is miscible with water and many other organic solvents. So the structure of oxygen is confirmed by the microwave and Raman spectroscopy, which allow to measure the bond angles and bond lengths. The COC bond angle is found to be 94.5 degree. The CC bond length is carbon-carbon bond length. There are two carbon-carbon bond length and two CO bond lengths. The carbon-carbon bond length is 1.54 angstrom units. CO bond length is 1.46 angstrom units. So coming to the methods of synthesis. Oxetane and its derivatives have been prepared by a number of general methods, like the first one is cyclization reactions, second one is Federnoguchi reaction, third one is from oxidanes. So this is cyclization of gamma halo alcohols. Gamma halo alcohols on cyclization reaction gives oxetanes. We know Federnoguchi reaction under photochemistry. It involves the addition of excited ketones to olefins to form oxetanes, and oxidanes, three-membered heterocyclic rings containing oxygen, are converted into four-membered heterocyclic rings containing oxygen by treatment with sulfur gases. Let us see these methods one by one. Cyclization reactions. So oxetanes are conveniently prepared by intramolecular cyclization of 1,3-halohydrines in presence of base. So this is alpha, beta, gamma halo alcohol. So and we can call it as 1,3-halohydrine. 1, 2, 3 halohydrine. So 1,3-halohydrines, when treated with a base, they undergo a intramolecular nucleophilic substitution reaction, resulting in the formation of oxetanes. The rate of the reaction, however, when halohydrine is converted into oxetane is very slow. Therefore, it is converted. Halohydrine is converted to its corresponding acetyl derivative. It is converted into OCO CH3. Then we can increase the rate of the reaction. The product formed is same, oxetane. It is also an internal nucleophilic attack of the acetate. The second method is the Federnoguchi reaction. So it is a photochemical cycloaddition reaction. The addition of carbonyl compounds to olefins forms oxetane. So Federnoguchi reactions involve addition of excited ketones. Ketones are excited and they will add to olefin. If the olefin is not symmetrical, we get with unsymmetrical olefins, we get two oxetanes. We can see variation in the position of this alkene. Here we can see CH3, CH3, and here HCH3, and here CH3, CH3 adjacent to oxygen and HCH3 here. Here HCH3, this carbon is adjacent to oxygen, and in this compound, this carbon is added to oxygen. So unsymmetrical olefin will result in the formation of two oxetanes. The formation of major product can be predicted by the formation of triplet biradical. Another important example is the reaction of cis and trans butenes. Cis and trans butenes react with benzophenone. The photochemical reaction of benzophenone with cis and trans butenes form a mixture of cis and trans oxetanes. So cis and trans 2-butenes reacts in a similar manner with benzophenone to form the same mixture of two oxetanes, trans oxetane and cis oxetane. So of these, the trans oxetane is the major product. Trans oxetane is the major product and cis oxetane is the minor product. So next, oxygens. From oxygens or methylene insertion. Methylene inversion. That is insertion of CH2 group between carbon and oxygen. Between carbon and oxygen, that is less hindered. So treatment of oxygens with sulfur ylides give oxetanes. The reaction involves methylene insertion from the less hindered side. So if the carbon is substituted, it is considered as hindered. If it is not substituted, it is considered as unhindered. So here CH2 insertion takes place between unsubstituted or least substituted or least hindered carbon and oxygen. So oxygens react with sulfur ylides. So this insertion of CH2 occurs between the less hindered carbon and the oxygen to form oxygen. So we can see here the two resonating forms of the sulfur ylide, and we can see the mechanism of this reaction where CH2 is added to the less hindered carbon atom of the oxygen to form oxygen. This is the mechanism. These are three important methods of synthesis of oxetanes, and let us see some chemical properties of oxetanes. Ring opening reactions. So the main important reactions of the 4-membered heterocyclic or 3-membered heterocyclic systems are the ring opening reactions by which they get relieved from the strain that exists in 3 and 4-membered heterocyclic ring systems. The most important reactions of oxetanes is the ring opening, and this can be affected by several procedures. Ring opening of oxetane can be affected by treatment with nucleophiles like methylamine, benzyl thiol. But both reactions occurs at very high temperatures. So this is oxetane reacting with the methylamine. This is methylamine. The ring opens. It is converted into OH, and here NHCH3 is added. And benzyl thiol. All these are bases. Benzyl thiol. This will open oxygen ring. We get OH and SCH2C6H5. Similarly, beta-naphthol. Beta-naphthol can act as a base and open this ring system. Beta-naphthol can also open this oxetane ring system. So these reactions occur at higher temperature on prolonged heating. Reaction with organometallic compounds. The oxetane ring can be opened with organometallic compounds like grignard reagents. So oxetanes reacts with phenyl magnesium bromide, a Grignard reagent, which after acid hydrolysis gives the corresponding alcohol. So 3-phenyl, 1-propanol. So this C6H5 will attack as a carbon nucleophile. This will attack at this carbon atom. It will attack this carbon, and this forms OMgBr, magnesium salt, which after acid hydrolysis is converted into alcohol. This is a Grignard reaction. Reaction of Grignard reagents with oxetanes. So reaction with acid catalyst. So acid catalyst can also open the oxetane ring system. So on treatment with HCl, it will form. So this is a substituted oxetane. It will form two isomeric compounds. So ring may be opened this side or this side. So if we look at these structures, ring opening is favored on this side. Ring opening is favored this side because this is the major product. This is the major product 94. Therefore, this can be formed only when this ring opens on this side. So similarly, acetyl chloride, it will also open the ring system on the same side, this side only. Here we must have oxygen. This oxygen remains as it is, and COCl is added as a acid. CO CH3CO plus. It is CH3CO plus Cl minus. So therefore here we must have O CO CH3. Here also O CO CH3. Similarly, when it is treated with aluminum chloride and barium, so the ring when we open to form a alcohol. Once again the ring opens on this side. Similarly, reaction with ethanol in presence of a trace of acid. So acid catalyzed ring opening by ethanol. Acid catalyzed ring opening by ethanol will also open this oxetane ring system to form a mixture of the two compounds. So ring will be opened on this side or this side. But ring opening on this side will is favored compared to this side. These are reactions with acid catalyst. Next, photochemical and thermal reactions. This is an oxetane derivative. It is an oxetane. It is formed by the reaction of benzophenone with 1,1-dimethyl allene. So 1,1-dimethyl allene is an alkene. It will react with benzophenone to form oxetane. This oxetane undergoes photochemical reaction in presence of triphenylene. It is used as a sensitizer. Triphenylene is used as a sensitizer to transfer energy to the carbon-carbon double bond. Here we can see the carbon-carbon double bond is excited. It forms a diradical. So it forms two. Then it is undergoing rearrangement to form another biradical. It undergoes rearrangement to form a different biradical, which will undergo cyclization to form a cyclobutanone. It is a cyclobutanone ring system. It is a cyclobutanone ring system. So alkene, so carbon-carbon double bond. So it is converted into C double bond O, and this oxygen is converted into a carbonyl oxygen. So cyclobutanone. Oxetane ring is converted into cyclobutanone. Similarly, another example here, pyrolysis of this is trans 3N propyl 3-phenyl oxetane. So trans 3N propyl 2-phenyl oxetane. This is third position. So 1, 2, 1. This is 1, 2. So 1 trans 2-phenyl, 3N-propyl. This is third position and this is fourth position. So this is a trans compound. These two groups are trans to each other. Trans 3N-propyl, 2-phenyl, oxetane at 250 to 300 degrees centigrade undergo pyrolysis, and this reaction is stereospecific and gives almost exclusively the trans 1-phenyl 1-pentene. So trans 1-phenyl 1-pentene. Here 3, 4, 5. On the from this side 1, 2, 3, 4, 5. So this is 1-pentene. So it is 1-phenyl 1-pentene. 1-phenyl 1-pentene. So the bulky groups are trans to each other. So therefore it is trans 1-phenyl pent 1-ene. These are some chemical reactions of oxetane. Photochemical and thermal reactions, reaction with acid catalysts, and some ring reaction with Grignard reagents and ring opening reactions. And under methods of synthesis, it can be prepared from the three-membered heterocyclic ring system. Oxirane can be converted into oxetane, and it can be prepared by Paterno-Bucci reaction, and it can be prepared from the halohydrides. This is about the oxetanes, different methods of synthesis and reactivity. These are some physical properties.